All right. Hello, everybody who's watching online. Welcome to our little kind of review session, kind of ask your questions and get them answered session before your final this Saturday. So we only got a few people here right now, but maybe some more will show up and we'll get more questions. But in the meantime, I'm sure we'll have plenty of questions for right now. So give me what you got. That's okay. Hey, that's fine. Okay. Number 22. Okay. So each time I'm going to list the number of the problem and what exactly it's on. So number 22 on, and this is on my study guide. Okay. So we're going to find, so the question is to find f prime of a, and then this is going to be using f prime of a is going to be the limit as x approaches a of f of x minus f of a over x minus a, and this is going to be whenever f of t is equal to t over t plus 3. Great. Okay. Back here for now. Okay, so this is a limit definition problem. And for those who are in the second recitation, you guys are, we actually got to go through an example of doing one like this, but this will be a bit bigger. But
would this be on the final?
yes,
What?
you could have one like this.
Well,
Okay, so it's good to practice this. I agree, for sure. So, because you need to understand how to use the limit definition of the derivative rather than just getting the derivative itself. So, what we're gonna do, right, is I'm just gonna plug in for each spot, right? So we're gonna take f prime of a, and so this is gonna be the limit. In this case, I'm using f of t, so I could use, oh, hello, welcome. We've got another person. Awesome. The limit as t approaches a of f of t minus f of a over x minus a for t minus a, my bad. Okay. And this is going to be the limit as t approaches a of, so f of t is going to be t over t plus 3 minus a over a plus 3 over t minus a. Great. So all we've done is just plugged in things, right? We've just I took f of t and plugged it in, and then f of a, and I put a in for the t here. Okay. So what's going to be my next step to carry this out? To take care, right? Because I basically, so I have t over t plus 3 minus a over a plus 3 over t minus a. I can't cancel anything right now, but that's okay. What could I do next? How could I try to simplify this? Any ideas? What is it? Okay. So I'm not sure if necessarily a conjugate would help in this case. What is it? Factor out the, oh, subtract. Okay, so subtract these. Okay, yeah. So I can't subtract them right now because one's a t plus 3 and one's a plus 3, right? So how do I fix that?
you multiply one by a plus 3 and the other by t plus 3.
Good. So I'm going to multiply. Yeah. So this term right here. So I'm going to rewrite this. The limit as t approaches a. So we're going to multiply. Okay, well, there's one here. I'm gonna make sure to pin my video just so in case someone does come, then well, I guess it doesn't matter right now. So we're gonna multiply t over t plus 3 times a plus 3 over a plus 3 minus a over a plus 3, and then we need to multiply this by t plus 3 over t plus 3. So, and then that's all over t minus a. Good. So this is going to give us the limit as t approaches a of, now, so we're going to get t times a plus 3, which I'll go ahead and distribute that, right? So we're going to have ta plus 3t minus, okay, so now we have minus a times t plus 3. So we're going to get minus at minus 3a. And that's all over on the numerator. We're going to have a plus 3 t plus 3. And then this is all divided by t minus a. Okay. What do we notice here? Is there anything that we can do? Anything that simplifies for us?
Wait, can you stop for a second?
Yeah, absolutely. Hello.
Okay, I got it.
You said 3 plus a? Okay. So let's notice, right? Remember, I have they're in different orders right now, and that was just because of how I distributed them, right? But isn't TA the same thing as AT? Right? Numbers are commutative in the way that we flip them around, right? So this term and this term are going to cancel each other out. Great. Okay. So this is going to leave us with, I'm going to go equals the limit as t approaches a. Now, let's notice that both of these terms have a 3 in front. So I'm just going to factor it out. So I'm going to have 3 times t minus a over a plus 3 times t plus 3. And this is all divided by, right, we have a kind of bigger fraction still, all over t minus a. Great. Okay, so I combine those fractions together, which is nice. But I still have fractions in my fractions, which is a real pain. So how could I fix this? Right, just turn it into one fraction and not kind of a mess of fractions.
Would you just multiply?
What is it?
Would you multiply like the very top numerator by t minus a?
Not quite in this case, actually. So remember, we want to think about this bottom, right? So we want to think of this as 2 fractions. The top fraction is this, and the bottom fraction we can think of as t minus a over 1, right?
Oh,
now,
so would you multiply the whole thing by 1 over t minus a?
Good. Yes. So we're going to do the limit as t approaches a of 3 times t minus a over a plus 3 times t plus 3 times 1 over t minus a. Okay. Sounds like someone's coming in. I'm going to let them in real fast. But do you see what's going to happen from this point? Welcome. So just to catch up, person who just joined us, we are solving this. So this is number 22 on the study guide that I made for you guys. We're essentially finding the derivative of this function using the limit definition. And so we went through, we plugged things in, we got a common denominator. These TA and AT terms canceled out. That left us with this when I factored a 3 out of the top. And then we could multiply the fractions together, which led us to here, right? Now what's going to happen? Good. This t minus a and this t minus a go away. So we're left with the limit as t approaches a of 3 over a plus 3 times t plus 3. Okay. Can I put in a? Now, is it safe? Yeah, because originally t minus a made it not work. We had a minus a, but now it's gone. So we can plug the a right in, right? So we're going to get the limit as t approaches a, or sorry, I plug the a right in, can I? So we're going to get 3 over a plus 3 times a plus 3, or more succinctly, 3 over a plus 3 squared.
Oh, I have a huge big confusion.
Where did you get confused from here to here?
Yep.
Okay, so why couldn't we plug in a originally?
No, what? Why is a t?
What is it?
Why is t turned into a?
Because we're doing the limit as t approaches a.
Okay, so only plugging it in for t, because the top says, okay.
Yeah, we just plug in the a for t, which we can do now since the t minus a term gone. So we get 3 over a plus 3 times a plus 3, or we get 3 over a plus 3 squared. Cool. And so that'll give us, it just said to find this, right? It didn't say for a specific value.
No.
Okay, great. So it's just this. If you were given a is 2, you could have also plugged in like 2 up in the problem itself and solve for it, or you could just plug it in down here. So in that case, it'd just be 3 over 2 plus 3 squared, which would be 3/9. In this case, we just had a general number a, some random a that made this work. Okay, awesome. So it's a bit of work just remembering how to do fractions essentially. And it is interesting that essentially it's almost as if that t isn't there. Because it just kind of disappears. But the quotient rule you would think would work in some weird way, but it cancels out. Obviously. Yeah. If a is 2? Yeah.
So.
Yeah. Yeah, so you can put, so we could directly just put like, if a was 2, I could have started out and just put f prime of 2. So I'd be doing the limit as t approaches 2 of f of t minus f of 2 over t minus 2. And then from there, I could actually this would just give me 2/5 over 2. So there might actually be a little bit of a simpler, it might actually go a bit simpler. Right, but this is for any a in this case, so no matter what a I have, I can plug it in. Okay, so and then from there it follows, but you do the same way. Okay, great. Now it's time for another one. Questions? Because there's a lot of things to go over, so there's really a lot of options here. I'm up for anything, even a water tank problem.
Nope.
What is it? Number 4. Okay, great. So, okay, so this is number 4. On my study guide, same place. Y equals sine. Thank you. So we were given this function. And I need to find the domain of this. I wanted to find the domain of this function, right? So in order to do that, we need to figure out where are the troublesome spots in this function, right? First of all, is there any point where sine of x can be undefined? Is there any x I can plug in the sine and make it undefined? No. What about tangent?
Yes.
Yes, there's quite a few of them, right? It's so what, give me one.
Is it pi over 2?
Right, yeah, so pi over 2 is a good example. Tangent x is undefined.
What did you say earlier? It was like everywhere where cosine something.
Yeah, so it's everywhere where cosine equals 0, right? And that's because tangent is equal to sine over cosine. So everywhere where cosine is equal to 0, that means tangent's going to be undefined. Okay, so that is exactly when x is pi over 2. What's another one?
Pi.
No, pi.
Wait, is it 3 pi over 4?
Not 3 pi over 4, 3 pi over
2.
2. Okay, and you can actually continue. 5 pi over 2 would be another option. 7 pi over 2, and even going backwards, negative pi over 2. Negative 3 pi over 2, etc. All of those would make tangent undefined. Okay, so if it's a pi over 2, if it's an odd multiple, pi over 2, right? 1, 3, 5, 7, -1, -3, it's going to be undefined there. Okay, so the best way to write this, right? What's the difference between each of these, right? So what's 3 pi over 2 minus pi over 2? Pi. What about 5 pi over 2 to 3 pi over 2? Pi. In each case, it's a pi of difference, right? So we're just going to pick one. So in this case, I'm just going to pick pi over 2. And then I'm going to simply say plus pi times n. Okay, which does make sense as well because tangent actually has a period of pi. That every pi tangent repeats itself. Okay, just like sine and cosine has a period of 2 pi, tangent has a period of pi. Okay, so that's why that pi makes sense. So no, and then n is malleus. The notation I'm using here basically just says n as an integer. You can write n as any integer if you want. I just like to do a shorthand sometimes to save some time, but so this makes it undefined. So these are out. We can't have these x's. Okay, they're not allowed. Okay, what else would be a problem with this function? What is it? Good. So we don't want the bottom to be 0, right? We don't want the denominator of this function to be 0. So we do not want 1 plus tangent x to be equal to 0. Okay, but that's exactly when tangent x is equal to -1. So what angles is this? Is this happening at? What is it? Not 5 or 6. So let's think about another way to think about this is that tangent, again, is the same thing as sine over cosine. So it's when those two things are equal. Do you remember what angle that was? What is it? 40, 45. Now what's 45 meridians? Pi over 4. So x is pi over 4 would be an option here. Okay. What's well, actually, in this, not quite, sorry. That's my bad. Pi over 4 gives us 1, right? But we want -1. So for those of you remember who were able to take trig, we would take, say, pi over 4 as our reference angle, right? So, and then I'm going to go from, right, which quadrant is tangent going to be negative in? It's positive in quadrant 3, actually. So it'll be negative in 2 and 4, right? And so we just look for our reference angles in those quadrants, right? Which this one's pretty easy. You could just literally just use negative pi over 4 in that case. What would this angle be? What is it? No, it's okay. So remember, this whole half circle is pi, and then we're subtracting a pi over 4 from it. So what's 4 pi over 4 minus pi over 4? 3 pi over 4. Okay. So you could also, since again, well, in this case, I think you'd have to put, sorry, I'm trying to. So we can actually notice if you kind of kept finding more, right? This is also the same thing as 7 pi over 4, right? Or we could also have negative 5 pi over 4 or negative. They're all a pi apart again.
I don't
Right.
see where we're going with this. I don't see where we're going with this.
Well, I'm showing. We're talking about some of the values,
okay.
right? So each time, each value is on this line right here, right? And how far is this? What angle is this from here to here? Pi. So again, each pi we're getting a value that makes this work. So again, let me just choose an angle. Easiest one being negative pi over 4, I think. And so we're going to write this. I'll write the dot here. We'll just say x is negative pi over 4 plus pi, and I don't want to use n again, so I'll use m. Okay, so there's quite a few options that make this thing that are in the domain, right? If you were to write down a final answer, you would say every x except if x is this or if x is that, where n and m are whatever integers you can think of. Okay, because this makes tangent undefined and this makes the denominator 0. Okay, is that good? I wouldn't assume you'd have one that have this many different spots that to worry about. But. Well, you would say, so the final answer would be, all right, FA, would be all real numbers except x is pi over 2 plus pi n, and x is negative pi over 4 plus pi m, where n and m are integers. That would be the final answer. Okay, so you're saying all real numbers except if the real number looks like that. If it looks like that, throw it out. It's gone. Take it. Get rid of it. Okay, so this is yeah, this one. Well, you wouldn't be able to notice the holes because they're only 1 point, but it does have a few. Cool. Okay. Any questions there? Oh, hello. We keep growing over time. I like this. Straight. Okay. Make sure there's no. Okay. Yeah. Cool. Okay. Yep. By the way, again, just for those who have my study guide, I do have an answer key, and so you can look over that if you need to check anything. Cool. Okay. I need more questions. Lay it out. I need something else. What do we got? What do we got? Yeah, absolutely. Okay. So so I'm gonna, just to give a problem as an example to go off of, I know number 3 is an example of this on my study guide. But we're gonna talk about this as a general discussion, right? So remember, an even function is gonna be something that looks, well, maybe not always exactly like this. You kind of want to have this sort of picture in your mind, right? Where if I took the right side of my graph and pulled it over to the other side, you would have the same exact picture. Okay, so this is an even function, and it's the same thing as being symmetric about the y-axis. Okay, so this is actually an important discussion because some integrals you run into can be solved easier if you understand the concepts of even and odd. Okay, so the nice thing about even functions, right, is notice that if I think about the number 1, right, and see where that, what about y value that gives me, then its negative value, which is -1 in this case, is going to give me the exact same value because, as I said, I twisted over that y-axis and it gives me the same thing. So if it's even, that tells me that f of -x is the same thing as just whatever f of x is going to be. Cool. Next, an odd function. I think a great example of this is, just to see as a basic picture, is x cubed. Okay, so x cubed is a good example of an odd function because if I take this end and rotate it 180 degrees around, rotate it around the origin, then it's going to look exactly like this end over here. So it kind of folds into itself. Okay, so when we're odd, that's being symmetric about the origin. Great. So if we're an odd function, right, unlike this case, I'm going to have 1. If I have 1 and that gives me whatever this value is normally, it'd be +1 in this case, right? Then if I go to -1, because it's symmetric about the origin, it should take me the same distance down. So in that case, instead of being +1, it'd be negative. Okay, and this is a general case. If I take f of -x, then that's simply going to be minus whatever f of x was. Okay, so in that case, f of -1 is just negative f of 1. Okay, so this is what it means to be an even function. This is what it means to be an odd function. Okay, if the only other case you can have is if the function's neither, which in that case, it doesn't follow either of these rules. So there's no clear symmetry, no clear piecing together. You might be able to like, maybe if you look at this axis, it can work, but around the nicer spot, it doesn't make sense, okay?
What was the trick or whatever for it again?
What is it?
What was the trick for it again?
For odd?
Like, was it something about if it was all odd number exponents? We didn't
Yeah,
talk about
yeah,
that.
oh, yeah. So, yeah, we talked about this real quick. So, if I have, so, and this is in the case of polynomials. So if I have a polynomial with even powers only, then it's an even function. And that comes from a very easy check of this, right? Because negative x would always be undone. It would just be negative x squared, which is x squared, right? And then if in this case, if I have a polynomial, polynomial with odd powers only, then it's an odd function. Which is clear in the case of x cubed, for example, because negative x cubed is the same. Negative x cubed, you can just bring out the negative one. And the same case would apply for all of those.
Does the exponent of one count?
Yeah.
Okay,
Yep.
so wait,
So this is 1, 3, 5, 7, 9. This includes a constant as well. The even function includes
so
constants.
x squared plus 2x would be neither?
Yes. Yeah. And a good way to check that would be to come back here. You had a question? Yeah, if it's a mixture, then it's going to fail the conditions. Okay, it's not going to be f of x, it's not going to be negative f of x. Okay, so the way to test this, right? If you don't have these little rules you memorized, is just to say, okay, well, let's take my function. So in number 3's case, it was 1 over x cubed minus x. Okay, so then I'm going to look at what f of negative x is. Well, in this case, f of negative x is going to be 1 over negative x cubed minus negative x, which is going to be 1 over negative x cubed plus x, right? But if I take a negative 1 and factor it out at the bottom, this is going to be 1 over minus x cubed minus x. Or I can just bring that negative up to the top or think about it in front, minus 1 over x cubed minus x, which is just f of x. Right? So we plugged in negative x. Negative x cubed is x cubed with the negative 1 out in front, minus negative x is plus x. I factored out a negative 1 out of both. That gave me x cubed minus x again. But then that's the same thing as just saying negative 1 times the whole thing, which is just minus f of x. Okay, so this is, what type of function is this? It's an odd function.
So I had a rational function.
Mhm.
Polynomial on top and polynomial on the bottom. And all of the exponents were odd in the numerator and the denominator. Would it be an even function?
Yeah,
Okay.
it would be. Because you would get negative on top and negative on bottom, which would cancel each other out. So yes. Anyway, yeah, I would encourage you to check using the little rules we have, but if it's easier for you to think about it this way, then by all means, let me try it out. But some functions like sine and cosine don't necessarily operate on the polynomial spectrum. So cool. Okay, so there's a quick, and let me just mention real quick. I don't think I actually put in a problem like this, which makes me sad, but if I take the integral from negative a to a of an odd function, and let's say it's dx, what is that going to be? 0. Right? Because we what's going to happen is that you're getting, in the case of x cubed, for example, the area that's up here is the same thing as the area that's down here. And so they cancel each other out. Okay. What about in the case if I'm going from -a to a and it's an even function? 2 times what? It's 2, and then I can just do one side. I can opt for one side. I can just go from 0 to a instead of even. Okay, so that actually makes it that's actually kind of a nice result, because think about, all the times where we've had to, if you have absolute value of x, for example, that's very clearly an even function, right? And so instead of doing the 2 different lines, in that case, you could just do one side and then just multiply by 2. So that would make your life a little easier. Okay, it won't always happen, but it's something to keep track of. Okay, cool. Questions about this before we move on to something else? Cool. Okay. Okay. What's next up? What do we got? Oh, okay. So, okay. Oh, and this is Newton's method. Is this one of the ones that you recommended you guys do? Okay, great. I just want to make sure. Show that the shortest distance from the point x1, y1 to the straight line ax plus by plus c equals 0 is. Oh, so you're supposed to do 39 and 40? Just 39? Sorry. Which one are we supposed to do? 39? Okay. And 40. Okay. Cool. So, Oh, okay. This isn't. I was like, this isn't okay. So these are optimization problems. Okay. I was like, I see this Newton method over here. It's not Newton. This is optimization. So this is probably a good example. Okay. So we're wanting to show that the shortest distance. So we want the shortest distance from XO, YO to, and let me write, this is number 39 in chapter 3 review. XO, YO, or X1, Y1, sorry, it doesn't matter. To the straight line AX plus BY plus C equals 0. Okay. And we want to show that it is the same thing as the absolute value of AX1 plus BY1 plus C over the square root of A squared plus B squared. Okay. So we're going to minimize the distance, correct? And so if we want to minimize the distance, we know that we have this equation, right? That puts X and Y kind of in terms of each other with some random constants, right? So we need another equation, which in this case is just going to be the distance formula. Okay. So I'm going to take any X and I'm going to take some X and Y in that graph, which is going to be what? So distance. So let's say on this line, we have the point XY. Okay. Then the distance between X1, Y1 and this XY point is going to be X minus X1 squared plus y minus y1 squared. Any opposition there? Any? Okay, so this is the distance formula, right? It kind of comes from the Pythagorean theorem a little bit because we notice this is the length of one side, this is the length of the other side, and then you'll get the hypotenuse between them. Okay, so we want to minimize, we want to get the smallest distance, the shortest distance, right? So I need to get this in terms of one variable. So what variable do we want to write in? Do we want to write it in terms of y or in terms of x? What do we think? Or sorry, we just solve this one for one of them, right? To get this one in terms of just one variable. So do you prefer to solve for y or solve for x? Y? Okay, we'll solve for y. So how do I solve for y in this equation over here? Subtract y.
Can we, wait, what's that second thing written up there?
What second thing? Here?
Nope, that.
This is, we're wanting to show that this distance is equal to this thing. So we're gonna do the work.
And then that should be the answer.
And then this should be the answer.
Oh.
Yes. Yeah, this should be the answer. I'm gonna make that clear here, separate that out. Yes, we don't know this off the bat. Okay, we're wanting to show that this is the case. So if I'm solving this, so we're solving this for y, right? So I heard we subtract. What do we subtract? Ax and c. So we're going to get by equals negative ax minus c. So what's y going to be? Divided by b. Or I'm going to write this as negative a over b x minus c over b. Just separate it out. Okay. So the b divides from each term. Okay. So we've actually had similar examples where we were talking about minimizing the distance. Let's not focus on trying to minimize the square root part because that's just going to be a mess. Let's just look at, instead of looking at the square root itself, let's try to minimize d squared, right? Because if we minimize d squared, then we minimize d. So d squared is going to be x minus, and I'll call that f. Why not? Just to give it a name, is d squared, which is going to be x minus x1 squared plus. Now we're going to plug in y, right? Which y is going to be negative a over b x minus c over b minus y1 all squared. Okay, now we have a bunch of constants, right? And then everything is in terms of x. So that's pretty nice. Okay, so we could either try to kind of square this out, multiply things, or we could just take the derivative here, which I think might be more beneficial to us. What do we think? We want to take the derivative here or wait until later? Let's just go and take the derivative now, right? So f prime. So what's the derivative of x minus x1 squared? Good. Times 1. So it's just 2 times x minus x1. Okay. Now what's the derivative of this guy? So it's 2 times all of this in here. That's to the first power, but then we need to multiply by the derivative of the inside. Well, there won't be, right? This is y1. Y1's a number, remember? So that's not, we don't need to worry about that. Okay, so we're just multiplying by minus a over b. Great. So now we can kind of like try to multiply things together and see if anything might simplify, right? Ultimately, what do we want this to be equal to?
Yeah.
Well, we want this to be equal to this. We want the f, we want the distance here to be equal to this guy. Right. I guess my question was, I have f prime right now, right? Which is d squared. What's my goal with this? What do I want this to be equal to? What do I want f prime to be equal to? If I'm trying to maximize or minimize the distance. Was it? We said it equals 0. Right? Don't get so caught up in all the constants and stuff and everything that we forget what our goal is here, right? When we're maximizing or minimizing, our goal is to take the derivative and set it equal to 0. That'll give us critical points.
So are we solving for x?
Yes, so we need to solve for x in this case. There's a lot of constants floating around, that's true. But it shouldn't be any arithmetic too bad. So we're gonna do 2x minus 2x1. And then I'm gonna go ahead, I'm gonna take minus a over b times 2 and multiply it in with each thing. So we're gonna get plus 2 a squared over b squared x. So that's 2 times minus a over b times minus a over bx.
Oh, gotcha.
And now we're gonna do 2 times minus a over b times minus c over b, which is gonna be plus 2ac over b squared. And finally, we're gonna do 2 times minus a over b times y1 times minus y1, which will be plus 2a y1 over b. We want that to be equal to 0. Yeah. Okay. So let's see. So we need everything with an x to be by itself, right? So I'm gonna get, and I'll go ahead and factor out the x as well. So we get x times 2 plus 2a squared over b squared equals 2x1 minus 2ac over b squared minus 2ay1 over b. Okay. If I can make a suggestion here, that'll make this easier to solve, right? Because if you notice, if we want to get the solve for x, so we'd have to divide. But if we divided right now, we're gonna have a whole lot of fractions to have to worry about. Yeah. Because so I added the 2x1, I subtracted the 2ac over b squared, and I subtracted the 2ay1 over b. Okay, so let's take everything in this equation, right? So what denominator am I seeing in each case? It's either b or it's b squared. So an easy way to get rid of all those b's is just to multiply both sides by b squared. Right? Because if I carry this inside here, I'm going to get 2b squared plus 2a squared. Hey, that's interesting. That we get 2b squared plus 2a squared, because that seems like we're on the right track for something here. And this is going to be equal to 2b squared x1 minus 2ac minus 2ab y1. Right. So x, what's x going to be? You don't have to read it out for me to say kind of what we're doing. I can write it down. So I need to get x by itself. So we're going to divide this from this side. So we get 2b squared x1 minus 2ac minus 2ab y1 over 2b squared plus 2a squared. Okay. What's in every single one of these terms? A 2. It's kind of obnoxious. I'm just going to you can divide a 2 from each spot. So I'm just gonna go ahead and b squared x1 minus ac minus ab, b squared, a squared. Great. Okay, so that is the x that will make this work. Okay, so from here, you should be able to, and I probably won't carry through just because it would take us a while. You should be able to plug in this x back into this equation, or maybe this one, take the square root, and get that exact. Okay, so cool. Let's do another optimization problem. Number 40. Can you? Not sure. Let's go back. Oh, there it is. Okay. So we want to find a point. So this is number 40 in the chapter 3 review. We want to find the point on a hyperbola. I find it weird to call that hyperbola. I mean, it is technically, but so we have the graph x y equals 8, and we want to find the point on this graph that is closest to 3, 0. This is going to be a lot nicer because we're not given a whole bunch of constants. We're just given some nice numbers. Okay, so this is going to be a breeze compared to the last one. So where we run into a similar idea, right? I want to minimize the distance. I want to find the smallest distance between this graph and this point. Okay, so I'm going to come from here and I'm going to pull out some random x and y point, right? And then I want to create a distance formula. So how do I represent the distance between this xy point and 3, 0? Mm-hmm. So you can say 0 minus y, or you can say y minus 0. If you put 3 minus x in there, it doesn't matter. It's squared, it's going to be the same thing. So the distance I can write is x minus 3 squared plus y squared. Wow, that makes it really nice. I just have y squared, not even a number. Okay. Once again, I'm wanting to take this, pin my video. I'm going to take this and minimize it, right? So the easiest way to do that is I'm gonna create another little function called d squared, which is just x minus 3 squared plus y squared. Okay. So right, we want to take the derivative, set equal to 0, get a minimum. But in order to do that, I need to get this right side only in terms of x. So how do I do that? What is it? Not yet. I can't set it equal to 0 and solve for y in terms of x here.
Solve x times y equals 8 for y.
Good. Yeah. So what's that going to be? Y is going to be 8 divided by x. And so I plug that in here. So I'm going to get x minus 3 squared plus, now if it permit, this is y squared, so it's going to be 8 over x squared, or just 64 over x squared. Awesome. So now we're going to take the derivative of this distance, or the distance squared in this case, and I'm going to set it equal to 0. So we'll do it. I don't need to multiply this out again. Let's just do it as is, right? So I'm going to get 2 times x minus 3 times what? Just by 1, yeah, because it's chain rule. And then what's the derivative of 64 over x squared? 128. So it's gonna be negative 128 over x cubed. And that's because I can rewrite 64 over x squared as 64x to the negative second power. The negative 2 multiplies down. I'm gonna write that 64x to the negative second. The negative 2 multiplies in front, gives us 128, negative 128, x to the negative third power, which is where the x is. Okay, that's just power rule. Okay, and then I want to take this thing.
I thought, wait a second.
Yeah,
Oh, no, never mind.
I'm going to take this thing, I'm going to set it equal to 0. So I'm going to get 2x minus 6 minus 128 over x cubed. 0. So this is a little bit of an interesting problem here. So let's take, I don't know, what's an idea? Let's get some ideas here of how I can go about solving this. What is it? Gotcha. Yeah, it may not help us too much right now. Let's see.
Can you wait, so
Yeah.
how did you get the 128 again?
So I got the 128 because y squared is 8 over x squared. So that's 64 over x squared. And then the derivative of 64x to the negative second power is 64 times negative 2, which is negative 128, x to the negative third power. Yeah,
I
so
just left it as 8 over x squared.
I guess it would have probably caused an unnecessary chain rule in that case, though. That would have been harder than this chain rule, right? Because this is just polynomial. In that case, you would have had to worry about, okay, 2 times 8 over x times negative 16 over 8 over x. It's just sorry. So I'm going to multiply everything by x cubed, so we can just get that guy off the bottom. Just figure out what's going on there. So I'm going to get 2x to the 4th minus 6x cubed minus 128 equals 0. Okay. Another thing I can do is all of these have a common factor. Have a number I can divide from each of them. What is it? 2. Good. So that'll give us x to the 4th minus 3x cubed minus 64 equals 0. Okay. So, in this case, I'm not really sure if I see much more than just thinking of, because this is actually going to have a nice answer. This isn't really one we can solve for easily. So let's just try to get some nice, like some smaller numbers that might make this work, right? I mean, 2 would be too small because we get 16 minus 24 minus 64. That's not true. 3 would give us 81 minus 64. That's not going to work. About 4. So 4. So 4 to the 4th power, 4 times 4 is 16, 16 times 4 is 64, 64 times 4 is 256. So we get 256 minus 3 times 4 cubed, which is 64, minus 64. Well, we have negative 3 times 64 minus 1 times 64. So that's minus 4 times 64, which was that. So this is indeed 0. So x is 4. Now, obviously on your test, you wouldn't have to guess that. You should be able to solve it easily. When it comes to quartic equation, it's I'm not sure if you can guess it. So x is 4 is our solution, right? So if x is 4 is our solution, right? Let's just real quick figure out what's y gonna be. So y is 8 over x, right? So it's gonna be 8 over 4. This is 2. Nice. Okay. So now if that's 2, let's just plug it into our distance formula. So the distance, so I'll write that over here. Distance is going to be the square root of x minus 3 squared, which we said x is 4. So we get 4 minus 3 squared plus 2 squared. So this is 1 squared plus 2 squared. So square root of 5 is our final answer. Okay, so a little bit more, I would say, involved of an optimization problem, but still nonetheless an optimization problem. Okay, can we see that clearly? Where we have this equation and this equation. So we use this one to get one variable in terms of the other one, and then minimize this one, which took a bit of a process, but we got there. Okay, I'll leave that up here for a bit. I have a request from a person on Zoom to do a couple of problems from the fall 18 final. So I'm going to pull that up for us real quick. Those will probably be a little bit tamer problems, so should be good. Oh, I didn't put in participation. Never do that. So let's see here. That's going to be under modules and 2018 final exam. Interesting. I figured they'd have a lot more than this, but okay. So number 6. Okay, great. So we're looking at another. Oh, gotcha. Sorry, my bad, Zoom. Another optimization problem, but this one's a lot easier. Okay. By the end of this, you're going to be so hammered in with optimization, it's going to be like second nature to you. Okay, so we have a box with a square base and an open top. So let's draw a box with a square base and an open top. Okay, so we have a square base here. I'll call this length and length, and then it has some height, and then the top's open, so I can put anything inside the top of that box. Okay, and it's given that the volume of this box is 4,000
What was the forming again?
cubic. What is it?
Square base?
Square base.
Okay.
Yeah. So the base is square, and then the sides have a random height attached to them. So it's 4,000. It says units cubed, so there's not any units attached to this. Okay. So it says we want to find the dimensions of this box that minimize the surface area. Okay. So first, what's the equation for volume of this box? Length times width times height, which is L times L times H, or just L squared H. Okay. What about the surface area of this box?
Wait, I was gonna say something about.
L squared is one of the sides. So L squared is the base, right?
Yeah.
Actually, only one, because box is open. Good. Because we have each of these sides are rectangles with an area of L times H. Okay, awesome. So I know that my volume, right, is 4,000. So once again, an optimization problem. I can use this one to solve for a variable. Which variable should I solve for? Good job. I would prefer to go for H rather than going for L in the square and everything. So H, I'll write down here, is going to be 4,000 over L squared. Anyone argue with me on that? Is that good? Okay. So now what do I do with this H?
Plug it in.
Good.
So wait, we're maximizing surface area here?
We're minimizing surface area, but you do the same
It's the same
process. Yeah, the process doesn't change because you're minimizing or
Okay,
maximizing.
how do you, I don't know how to ask it. How is it the same? Why is it the same? I don't
Because,
understand.
well, it's basically what ends up happening, right, is you're getting a function, you're turning one of the sides into like a function, right? And so it typically in these problems, whenever are given a volume and are solving for the surface area, the surface area function is actually going to look something like, at least in the area we're concerned about, is going to look something like this. Okay, maybe not exactly like this, but of some form of like it's curved up. Okay, so when we take the derivative and set it equal to 0, it's going to be a minimum because we're kind of, it's concave up in that case, right?
Okay, so we're minimizing here, right? Just
Yeah.
to be clear. What would we do differently if we were maximizing?
If you're maximizing the surface area,
Yeah.
well, that wouldn't take a lot of calculus. You could probably do that probably pretty easily.
Okay, so there's not gonna be only one way that it makes sense?
Yeah, there's only gonna be one way it makes sense, right? Think about if I have, if I'm given so much surface area and I want to, normally I'm asked to maximize the volume, right? But if I were to minimize the volume, well, then I wouldn't use most of that surface area. I would just use like barely any of it because then it would be minimized, right? So there's like a logical direction in each case. Okay, so the surface area equation ends up being L squared plus 4 times L times H, which is 4,000 over L squared. Okay,
So equal to 0? Is it time for that?
not yet. We have to, we need to take the derivative first, right? Before we say it equals 0. But let's go ahead and simplify this down one more time. So what's 4 times 4,000? 16,000. And then this is, we have 1 L over 2 L's, which just leaves us with 1 L at the bottom. Now let's take the derivative. What's the derivative that's going to look like? 2L, good, because that's just L squared becomes 2L. And then, so this is going to end up being minus because, right? So I'm taking the derivative of 16,000 times L to the minus 1. So the negative 1 comes down in front. So we get negative 16,000 times L to the negative second power. Because you subtract 1 from the power. So we get minus 16,000 over L squared. We're going to set this equal to 0. Now notice, this seems like a bit of a similar predicament to where we were in the distance case. But in the distance one, we had an extra constant there that made everything, or extra term that made it so it wasn't nice. In this case, once I multiply, so let's multiply both sides by L squared. Right? Let's go ahead and get that pesky L squared off the bottom there. So that's going to give me 2L cubed minus 16,000, 0. This is a lot easier to solve. You don't even have to guess in this case. It's pretty straightforward here, right? So how would I solve this? Well, we're going to add it, right? Because it's already subtracting. So we get 2L cubed is 1,600. Next. Divide by 2, which gives us L cubed is what? 8,000. Good. Yes, so through a little bit of work, you can see that that's L is just going to be 20. Okay, because 2 cubed is 8, and then if you just put a 10 on it each time, it'll be 20. Okay, so it asks us to find the dimensions. We already have one of them though. There's only 2 dimensions. There's L and there's H. So if I have L, how do I find H? So I'm going to get H is 4,000 over 20 squared. What's 20 squared? 400. So we get 4,000 over 400. Which is what?
2, 6,
Okay. So the dimensions of the box are 20 by 20 by 10. Okay. Do we like this one better than the
I like
the other
this.
ones?
I like this.
Yeah, this is more akin to what you get on the final. But the other ones are obviously optimization problems, so it's good to get in the mindset of what you're doing. So, yep, this is all. Okay, and we also have a request for number 13. What is it? Oh, what was the question asked? Oh, yes, sorry. This is number 6 from fall 18 final. I probably should have done that. My apologies. Okay. Great.
Is there, I have a question. Is
Huh?
there no spring California?
I think no, I'm not
That's what I was
sure.
thinking.
I'm not sure if okay. What I think is I don't think that there's a spring regular Calc 1. There's no 165 in the spring.
Oh, okay.
There's other Calc 1 classes, but
Gotcha.
that are 165. And I think that's because they expect that most people will end up taking 165 in the fall. It's not going to happen very often that someone ends up taking 165 in the spring.
Gotcha.
I was confused about that earlier too, because I was wondering if there were any
I know, I
S17s
saw
or.
that. It's like, oh, 14.
Okay, next one is number 13 from the same final. Wait, it's another optimization problem?
No,
Okay.
no, it's a rotate problem. It's a wash.
Oh,
It
okay.
just says to set it up too. That's.
Nice.
that's fine.
Isn't that nice? Yep, that's how most of those problems are going to be on the final.
And
So,
that's when there's a wash, and there's a-
oh yeah, so it has you set it up 2 different ways. Okay. Okay, so we have R is the region bounded by y equals x squared and y equals 2x. Okay, so tell me, what is x squared? It's a parabola. Good, so that's gonna look something like this. And what's 2x?
That's a line.
It's a line.
Hey, at least it's not hard
So this it's gonna look something like this.
to draw.
And we're asked to do this 2 ways. The first way, which I'll put, I'm gonna make sure I can see my screen here. So this is the region, this region right here is the region R we're referring to. So they said to do this 2 ways. First is to do it about x-axis with disc or washer. And the second was about the y-axis using chuck. Okay, so the 2 like most basic uses of each method, which is nice. Okay, so that we're pretty well set up, right? So here's our, let's kind of get a picture where our rectangle is at on here, right? So our rectangle is going to be vertical. Why is it vertical? Right, and well, for disc and washer, right? In this case, since our functions are in terms of x, then we want to use dx, which is going this way. So we want the small end of the rectangle to be here, and the larger end to be this way. Okay, so for disc and washer, we need 2 things, right? What 2 things do we need? Or I guess in this case, is this going to be disc or is this going to be washer? This is going to be washer. There's clearly white space in between the line we're flipping around. So we're going to need a washer in this case. For washer method, I need 2 things. What are those 2 things? An outer radius, which I'll label as big R, and an inner radius, which I'll label as little r. Okay, so the outer radius, right, is exactly as it sounds. It's the radius that's farthest away in general from the axis we're rotating around. So what is that function in this case? Good. So 2x. And that's because 2x is farther out from the x-axis. Okay, its values are bigger than 1x squared, right? Speaking of x squared, what's the inner radius? It's x squared. Okay. We good here? Does this make sense? Outer radius is 2x, inner radius is x squared. Great. So then what is our integral going to look like? It's going to be, our volume is, so pi.
Go from 0 to.
Oh, we need to figure out what the intersection point is, don't we?
Oh, yeah, I already did that.
So we're going to subtract 2x from both sides. I think I heard someone say that. We don't divide x. You know, that's a big no-no. We're not going to divide x from both sides. And so we have x squared minus 2x is 0, which is the same thing as x times x minus 2 is 0. So what are my two intersection points? 0 and x is 2. Good. So those are our bounds. Okay. What goes first? Big R squared, or I can just write that as 4x squared. Yeah. Yep. If you're doing disc or washer, there's always a pi out in front.
Wait.
What's 4x?
I like that better.
I figured. Okay, so we have big R squared minus.
X squared.
Good.
Those
And
are
then we throw the
multiplied,
x.
right?
What is it?
Those are multiplied?
The powers?
Yeah.
Yeah.
I think I messed it up. I don't even remember doing one of the problems from the hand.
So if you were to square each term, it would look like this. Okay. I definitely think you could probably leave this and be good setting it up, but this is also.
So that's all we need to set up?
Yep, that's it.
That's it? That's it?
That's it.
All right.
So that is the problem.
I'm ready for it.
Okay. Now we're gonna do about the y-axis. So now we're gonna, yes. What is it? You want this to be negative? I would try again. I'm not saying that it should be a positive value because you're gonna get, so when I integrate this, so the pi off to the side, you would get 4/3 x cubed minus. Oh. Gotcha. Okay. That would make sense. Okay. I was like, whoa. Pretty sure this is good. Now we need to do shell about the y-axis. Okay. So whenever now we're flipping around this axis. And we're doing shell method. We need two things for shell method. What are those two things?
Height.
We need a height and we need a radius. Okay. How do I get the height? What is it? Not quite. So our height. So we're wanting. So when we're talking about height in this case, right? We're wanting to get the height of this rectangle. How do I find the height of that rectangle? Right? It's going to be the height of the top of the rectangle minus this bottom part that I'm cutting off. Right? So what is the height at the top of the rectangle? Do it. Okay. What's the height here that I'm cutting off? X squared. So if you want to think about it, the height, when you're doing shell method, the height is very much how, what it's like when you're getting the area between two curves. You just subtract the higher curve from the lower curve. Okay, what about the radius?
I think that's X.
It's just X.
Because it's touching where it's rotating around.
Right, well, not even just because it's touching it, it's because we're just going about the y-axis. So it just needs to be X. Why is it just the radius equal to X? So the radius is going to be X because the radius in this context is going to be the distance from the axis that we're rotating around. Okay, not dependent on whatever the function is, just in general. Okay, so I can represent that distance by just saying X, right? So if I'm 1, then I'm a radius of 1 away from the axis. Okay, so shell. What is the shell method equation going to look like in this case? Two pi. So I'm gonna put the 2 pi out front if that's okay. And then it's the same bounds. We're gonna use 2 pi, 0 to 2, and then what's gonna be on the inside? RH. Yeah. So I'll take x times 2x minus x squared dx. And if you want to be extra fancy, we'll write 2 pi integral from 0 to 2 of 2x squared minus x cubed. Yeah. That's it.
We have a question.
Yeah. Question. I'm happy to answer.
It's from 2017. It is number.
Oh, you got like a question to do. Gotcha. Is this good here? Does this make sense to everybody? Okay. I feel like this should be pretty straightforward. I'm setting this up. But it's good to see you're not crazy. You do indeed just set it up and you're done. So no need to worry there. Okay.
So limit.
Okay. Can you tell me which? So this is question number
2.
2. This is question number 2. Okay. From fall 17.
Yes.
Okay. And so it's the limit. Oh, give me a moment to answer this. It's not going to be dy. You do not need to, whenever we were doing that integration, everything that we had was in terms of x, right? If I go between disk and shell, that doesn't automatically mean I choose y or I choose y in one case or I choose x in the other case, right? Most of the time it's dependent on what your variable is that you choose what the method is, right? So in each case, right, since I was flipping around the x-axis, they said use disk for washer, because in that case I can leave it as dx. When I was going about the y-axis, it said use shell, because that allows me to leave everything in terms of x. Okay, so there's no correspondence between disk use dy or disk use dx and shell use dy. So you don't need to change it in terms of y. Okay, so the limit is.
Oh, I thought you were just reading it. There's an upper fraction and lower fraction. The upper one
I
is-
could look it up. I just thought you were gonna
no,
tell it to
it's
me.
1 over x squared
Okay.
minus 1/4, and then all of that's over x minus 2. And it's as it approaches, it's as x approaches 2.
We've actually heard of a problem like this today.
Today, I was not.
Yep. Let me now you don't have to like immediately recognize it, but notice if f of x is 1 over x squared, then f prime of 2 is going to be the limit as x approaches 2 of f of x minus f of a over x minus a.
I don't want to do that though. Is there any other way that we can do that? Is there another way?
And besides doing this?
Yeah.
Yeah, absolutely. I was just showing you this is actually the limit definition. So technically you could just do you could just take the derivative of this, which is -2/x³, and then just plug it in 2.
What? Oh, no, stop, maybe I like that.
But we're gonna do it as it's presented to us, okay? So, but just something to keep in mind, I mentioned that, I can't remember which class I mentioned that in, but a lot of the limit problems you do in the first chapter are secretly derivatives. Funny enough. So, okay, so to solve this, right, I need to fix this x-2 problem. Okay, so I need suggestions. What do I do first? What ideas do we have? What option? What thoughts?
What do we do with the x-2? Is that what you're asking?
No, let's just start. How can I start
Oh.
this problem?
Try plugging it in. It
Okay,
doesn't
that's
work.
very true. It doesn't work. Especially it gives us 0/0, so it really doesn't work.
So is the limit only 0 when only the numerator equals 0?
Yes. Only when the numerator is 0. If the denominator is 0, then we got a problem. Okay, so if you remember the problem from earlier, it was for those who were here, it was the very first one. It was like, t/t+3 squared. Why don't we just try to get a common denominator again on the top? So I'm gonna multiply this guy by 4, right? And I'm gonna multiply this one by what? x². So this is gonna be the limit as x approaches 2 of 4 minus x² over 4x², all divided by x minus 2. Okay, is this good? Do I need to show the transition here? Okay. Well, now,
I remember this now. It was not fun.
yeah, that one was a little bit harder though, because we weren't given a number. In this case, we were given 2, right? So in this case, it's a little bit easier. Okay. Do I notice? Okay, so I don't know. I mean, there's a couple options here. Maybe let's try to fix it. It's another fraction and a fraction. Maybe let's try to work that. Let's try to fix that. So how can I rewrite this? X minus 2. So yeah, so remember, so this is technically x minus 2 over 1 in this denominator. And so using keep change flip, that means that I can just take this top guy and multiply it by the reciprocal, which is 1 over x minus 2. Now let's hone in, let's focus in on this guy. This should look somewhat familiar. What is it?
Yeah. This one.
It's 2 squared minus x². So what is that?
2 minus x. 2 plus x.
It's the difference of squares, right? Good. So that 4 minus x² is just the difference of squares. Okay. So we're in a little bit of a dilemma still. I almost can cancel this thing out. We have 2 minus x and x minus 2. They're just off by a minus sign, right? Because this is 2 minus x is just x minus 2 times -1. So how could I fix this? What is it?
Multiply like the fraction that needs to be, this needs the sign.
Okay, so maybe multiply this guy? Okay, so
Why don't you have to do that?
why don't you have to do both?
Yeah.
Well, if you did both, then you would make this one 2 minus x and this one x minus
That's
2.
what I'm saying, but why don't you do that?
Well, then that would lead you back up in the same place you were, right? We're 1 and 2 cancel these out. And so if I make this one 2 minus x and this one x minus 2, I can't cancel them out again because they're not the same thing,
Okay.
right? So
I will go with that.
Am I understanding your question correctly?
I have no idea.
Yeah.
Okay. Okay. So let's go ahead and take this fraction over here, just multiply the top and bottom by -1. So we get the limit as x approaches 2 of 2 minus x, 2 plus x times -1 over 4x squared. And I'm gonna go, I'm gonna go ahead and multiply that term kind of in. It doesn't need to be kept separate like that. Okay, so now I have 2 minus x. What can I do with that now? Boom, boom, they're gone. Okay. So that's gonna give me the limit as x approaches 2 of -2 minus x, because I just multiplied this -1 in with those terms, over 4x squared. Can I plug in 2? Great. So what am I gonna get when I plug in 2? -2 minus 2 over 4 times 2 squared. -4 over 16. -1, 4. Not -1/2. Okay. So that's our final answer there. -1/4. There was a weird spot before. Okay, just to show you what I was talking about. If you're able to recognize that this is a derivative. Watch this.
I'm gonna tell you right now that I don't understand at all what just happened. Can you like say that in words?
Yes, absolutely. I wanted to show, like I said, I think you should do it like this still, but it's a good way to check the answer. So this is secretly the definition. If f of x is 1 over x squared, then this is f prime of 2, which is f of x minus f of 2, or sorry, f prime of 2, which is the limit as x approaches 2 of f of x minus f of 2 over x minus 2. This is that. That is just the limit definition of the derivative. So if you happen to catch that, then I can just take the derivative of 1 over x squared and plug in 2. It's -1/4, which is exactly what that is. Now, obviously, we can evaluate that limit, but it is useful sometimes when maybe you have like sine or something, and sine won't necessarily work out. So I would just encourage it. Maybe a good way to check if you can catch it. If not, this is fine because this is probably how you're supposed to do it.
I'm sorry, can you say that again?
Say what again?
The check part.
So if we say f of x is 1 over x squared,
Okay,
f prime of 2, using the definition from earlier, is the limit as x approaches 2 of f of x minus f of 2 over x minus 2. But that's exactly what this is,
Mhm.
right? So then this thing is just the derivative of f, which is 1 over x squared. Right? And then I plug in 2.
So you find the, so wait, find the derivative of 1 over x squared?
Yeah.
And then plug in 2?
Yeah. As like I said, it's just to check. This is you can do this and be completely satisfied. I was just showing this as an option just to show, hey, look, there's the derivative. Okay. Cool. Oh, okay, we got another one.
I have to go.
The limit as n approaches infinity. Okay, so this one. Okay. Great. Well, thank you for coming. Appreciate it.
Yeah.
As always. Okay. Can you? So this is number. Which number is this?
3D.
Number 3D. Okay. So this one actually. Yeah, from fall 16. Okay. So this is number 3D from fall of 16. So this one actually works in a similar thought, but it's easier to recognize, okay, as to what just happened in the last problem, right? So we are taking the limit as n approaches infinity of the sum from I equals 1 to n of 1 plus 2 I over n times 1 over n?
Yeah.
Okay. So for those who really, really enjoy evaluating this using like, you know, getting saying I is n times n plus 1 over 2, by all means, I encourage you, go ahead. But what is this? This is the definition of something. We have a sum, there's a limit, it's an integral. This is a definite integral. Is it not? Where xi is this 1 plus 2i over n. And this, so in this case, so we're missing, it's a little bit off, we can fix it, right? Because delta x, if xi is this, then delta x we expect should be 2 over n. But it's not quite 2 over n. That's all right. Why don't we just throw 2 on the front here and then put a 1/2 out front. Okay, so if xi, so remember, for our general definition of xi and delta x, right? This is supposed to be equal to a plus I, plus I times delta x. And this is supposed to be equal to b minus a over n. Okay, so what can you guys tell me about a? A is 1, good. What can you tell me about b? B has to be 3, good. And that's because, so a is 1 clearly corresponds. And then we need b minus a to be 2. So that means b must be 3, okay? And so then what's our function? Maybe not. So this is, so remember, so let me rewrite this as kind of what we've defined already. So this is the limit as n approaches infinity of sum from I equals 1 to n of xi times delta x. Right? It's just x. My function is simply just x. Cool. Awesome. So this is going to give us 1/2. Right? Now we have all our things for a definite integral. This is 1/2 times the integral from 1 to 3 of x dx. Right? Because we have a is 1, b is 3, and our function. What is the integral of x dx? So it's going to be, so we have 1/2 times 1/2 x squared. We evaluate that from 1 to 3. So we get 1/4 times 9 minus 1. Right, because 9's 3 squared minus 1 squared. And so this is going to be 1/4 times 8, or just 2. So let me real quick how f of, yeah, so let me real quick, I'm going to recap this problem, okay? So I'm not just going to be like, okay, great, we got it, because I understand. Let's kind of think through this real quick, okay? So this is a very key thing in that you want to be able to know what your definitions are, okay? I know at one point you're just like, oh, I mean, I don't need to know the definition anymore. Your life's going to be easier sometimes if you know what those definitions are, right? So we start off and we are given this limit, right? Which is the limit as n approaches infinity of one of the sum from I equals 1 to n of 1 plus 2i over n times 1 over n, right? This should immediately be ringing, like, be looking familiar, because this looks just like the definition of our definite integral, right? This looks like, we have the sum, we have a limit, and then as we can see, there's a pretty clear looking xi term and delta x term, right? Now, we did have to make a bit of an adjustment for that delta x term, but that's okay, because I can just easily throw out 1/2 in front and put a 2, okay? That 2, those constants can, just like with derivatives or integrals, can kind of phase in and out of the sum of or the limit, okay? Yes?
No, it's not, that's not right.
Huh?
That's not right. No.
Well, we said xi was what? We said it should probably be this thing, which is 1 plus 2i over n, right? Xi is supposed to be a plus I times delta x. So if we have 2 over n times I, what do you think delta x is supposed to be? It's supposed to be 2 over n, right? So the reason we introduced the 1/2 and the 2 is to get that 2 over n in, okay? Now, you could also, if you want to, we can just simply say that xi is just I over n, and I think you could make that work as well. I might present that real quick in a bit, so I'll talk through that. Maybe that'll help us to understand the problem. So this completely works. Feel free. I'm sure maybe some of you have written this down. You people online can just pause and watch it probably for a bit, or even when you guys go back, you can pause and watch it. But if that's it, but what we can also do is I can just simply say that xi is just I over n. Okay, it's bare minimum. That's what we need. We need a plus I delta x. What's a going to be in that case? What is it? 0. Yeah, so we just say there wouldn't be an a starting point. Okay. So delta x then is what? Sorry, I want to write out this definition real quick. So we said a is 0, and we have I times 1 over n. So delta x must be 1 over n. Okay. So in a way, this actually fits a bit better. Okay. So in this case, we're going to replace everything again. So I'm going to get the limit as n approaches infinity of the sum from I equals 1 to n of 1 plus 2xi delta x. Okay. Whereas last time, and I just answer Robin's question on there. So this is in the alternate universe option we did here. When xi was 1 plus 2i over n, and delta x was just had to be 2 over n, then we could rewrite our sum or our limit as the limit as n approaches infinity as the sum from I equals 1 goes to n of xi times delta x. Right? Now, in either case, the normal way of looking at the sum is that I need to have, so the integral, it's defined as the integral from a to b of f of x dx is the limit as n approaches infinity of the sum as I equals 1 goes to n of f of xi times delta x, right? So in this case, we had xi delta x. So f of xi had to be xi. So that's where f of x being x came from. It was just that we needed f of xi to be xi, which meant that f of x was x. In this case, we want f of xi to be 1 plus 2xi, or f of x is 1 plus 2x. Are we following? Is that good? 1 plus 2x, right? So f of x needs to correspond to whatever this thing is that's in front of the delta x, which in this case is 1 plus 2xi, in that case was xi. Okay. So we said a is 0. What's b? What does b have to be in this case? Right. Remember, delta x is the same thing as b minus a over n. Right. All this is a memory definition. Okay. So delta x is b minus a over n. So b has to be 1. So we have a is 0 and b is 1. So that leaves us with this limit being equal to the integral from 0 to 1 of 1 plus 2x dx, which is going to be, what's the integral of 1 plus 2x? X plus x squared. And we evaluate that from 0 to 1. So 0, we'll just make that 0. So we just get 1 plus 1. Hey, that looks familiar. We got that earlier. Okay. Yes. So we said a has to be 0 in this case, right? So delta x is the same thing as b minus a over n. So we need 1 to be equal to b minus a. So 1 is equal to b in that case. Okay? Okay, now just to kind of address, what if I don't remember the definition? What if I forgot that part? Okay, well, hopefully you remember one of those transformations, which is that sum from I equals 1 to n of I is equal to n times n plus 1 over 2. Okay? Because in this case, right, let me take this sum and I'm going to multiply out that 1 over n. Okay? So this is equal to, sorry, I should put this up. Probably put that over here. But this is equal to the limit as n approaches infinity of the sum from I equals 1 to n of 1 over n plus 2i over n squared. Okay. Now, actually, I guess we need to know another one, right? I can rewrite this as the limit as n approaches infinity of the sum of from I equals 1 to n of 1 over n plus the sum from I equals 1 to n 2i over n squared. Okay. That's completely fine. You can split up the sums like that. Okay. There's no worry there. What's going to happen to this sum? It's the limit as its sum from I equals 1 to n of 1 over n. Was it? Not quite. So let's write this one down again as well. So if I'm going from I equals 1 to n of just 1, it's going to be n, right? So if I kind of bring out, let me rewrite this again one more time so you can see this clearly. This 1 over n and this 2 over n squared are just constants. So we're going to get 1 over n times the sum from I equals 1 to n of 1 plus 2 over n squared times the sum from I equals 1 to n of I. And now we say, those look more familiar to me. Okay, the sum from I equals 1 to n of 1, just n. So we get the limit as n approaches infinity of 1 over n times n, which is just 1. Okay, and we have 2 over n squared times the sum from I equals 1 to n of I, which is n times n plus 1. Great. So now this becomes just a natural limit problem, right? So this 2 and this 2 happily cancel each other out. One of the n's happily cancel each other out. So we're left with the limit as n approaches infinity of 1 plus n plus 1 over n. Someone want to tell me what the limit as n approaches infinity of n plus 1 over n is going to be? It's 1. So it's going to be 1, right? Because if you want to think about it, right, we're going towards infinity. so I get to divide the top and bottom by n, right? So I'll do that real quick. So the 1 is just gonna kind of come along, right? The limit of n approaches infinity of 1 is just 1. Plus the limit as n approaches infinity of, now let me take n and divide it from the top and bottom. So I'm gonna get 1 plus 1 over n over 1. Okay, this and this is the same thing. I just divided it on the top and bottom. So now what is this limit? It's 1 plus 0 over 1. It's just 1. So we get 1 plus 1, which is. Okay, so there's 3 different ways to do this problem. You pick which one makes the most sense to you. All of them are valid. I do think that seeing it as the integral makes it a lot simpler and can make it a lot simpler, especially if you get something more than just I, in case you get I squared or I cubed inside your problem. But this really wasn't too bad. Okay, there's a little bit of pulling out constants, but notice each time we got 2. Okay, so if you were unsure before, the correct answer is definitely going to be 2. Okay. Good. Good. Thank you for the problem suggestion. What? You want to do, okay, so hold on, give me a second, yeah, so we have a special suggestion from the audience here. And the question is to do 2 plus 2. Okay. Now, I personally, the way I would like to do this is I kind of see this a bit more as this is the same thing as 2 times 2, right? Because you're saying 2 plus 2, you're adding it 2 times, so it's going to be 2 times 2, right? Now, I think this would be pretty convenient to see this as 2x evaluated at x equals 2. Okay, so now. But also 2x is the derivative of x squared, correct? So this is the same thing as the derivative of x squared evaluated at x equals 2. Okay, so it's at this point that I think it makes the most sense that it's going to simply be so. Thank you for the problem suggestion. I appreciate it.
You're starting before you started.
I would have done more, but I didn't want to be too going too long with the joke. So yeah. Oh gosh. I don't even completely understand set theory sometimes. Don't ask me that. Okay. Suggestions. Okay. 5 on the 2014. Okay. Yeah, that'd be nice. Okay, give me, it's fall 14, right?
Yeah.
Okay, and it's x squared y plus y cubed equals plus 1
equals 3x cubed.
3x cubed. Okay, and there's a point. 1. Right. My favorite thing is the unnecessary addition of this one right here. Well, actually, and then you could just make that too. Anyway, okay. So this is a tangent line problem. What 2 things do we need for a tangent line? We need a slope and we need a point. Oh wow, look at that. We already got the point. That's good. We already got the taken care of. See, I always like to start with that because people will be like, oh that feels really nice. We already have the point. I love that part's taken care of. Okay, now the harder part comes. We have to do this fun slope. Okay, so, but there's no cosines or sines or anything in here. So it's, you know, there's a little bit of work, but nothing too crazy. Also, there's a little bit of an easier way to find the slope than having to solve for it completely, right? Let's talk about that. Let's take the derivative of this function. So I need to do d over dx on both sides. Okay, you don't have to. It's not necessary. Okay, so what is the derivative of x squared y? So 2x y, okay, that's part of it. Not yet. Not here. Okay, we have a function of x times a function of x. So we have to use product rule, right? So product rule says that I'm going to have the derivative of the first times the second, which is 2xy, plus the derivative of the second term times the first. What's the derivative of y? Y prime dy over dx, whichever one you prefer. For the sake of this problem, I'll just call it y prime. Okay, let's make our writing a little simple. We'll just say y prime. I know you guys are trying to write at this point, probably to solve the problem. So, okay, what's the derivative of y cubed? Good. What's the derivative of 1? No, yeah, that's right. No way, no. Okay, what's the derivative of 3x cubed? What is it? 9x squared. Good. Okay, so we have a couple options here. You could solve for y prime and then plug in the numbers, or we could just plug them in right here. Whoa. Solve for y prime. Yeah. So let's plug in 1 into this, right? So I'm gonna run around on the right here, plug in 1. Okay. So what's 2 times 1 times 1? Nice. What's 1 squared? 1. So we get 2 plus y prime. What's 3 times 1 times 1? What's 3y prime? And what's 9 times 1 times 1? 9. So I'm gonna get 1 plus 3, 4y prime, 9 minus 2, 7. So what's y prime? Wow, that just made these problems a lot easier, huh? I guarantee you, like if you went through and solved for y prime, it'd be the same result. Remember? You did it? Nice. So it kind of cuts out a little bit of the process, right? Because in the end, right, if you plug in an x and a y, then you're going to get a certain y prime for it as well. So, okay, look, we have the slope and we have the point. We did it. Let's just plug it in the formula. Yep, point slope formula. So we get y minus 1 equals 7/4 times x minus 1, which is y minus 1 equals 7/4 x minus 7/4, which we can write as y equals 7/4 x. Negative 7/4 plus 4/4.
Oh, I thought this was, we left this in.
You work this in. Huh. I know we didn't do this one exactly because we didn't do an implicit one, but maybe it just ended up being the same line or something. I don't know. It's possible. Does that make sense? Great. This is pretty fun one, huh? Not too bad. Okay, this problem. Gotcha. Did he have you solve for the y prime?
I know I did.
Oh, okay. Awesome. Here we go. You got another tangent line one right here? Oh, it's by yours truly. Um, yeah, okay, let's do it. Sorry, I had to think about it because okay, so this is number 21. Is this helpful, by the way? Like, is this
It's hard.
Dude, I'll do a couple on the regular. And I'll just-
gotcha?
Yeah.
Okay. I tried not to make it too hard, but what is it? Yeah, already with this. Yep, I imagine if you make it all the way through that, then I'm sure you'd be good to go. No doubt about it. You heading on out? Yeah, no problem. Thanks for stopping by. Okay, I just lost my problem. Okay, great. Okay, well, I'm sorry I made a bit of hard problems, but you know, it gets you real tough. You get real tough skin, and you're gonna be ready for Calc 2. You're gonna be like, I did a 100-question study guide for calculus. You don't even know, man. I'm ready for this. Okay, so we're going to find. So this is my study guide. I should write that again. So we're going to find the equation of the tangent line to the curve y equals x cubed minus 2x minus 1 at the point 2, 3. But there's a catch. You have to find it using the formula, the limit definition of the derivative. In this case, we're using 2, right? So we're going to do x of f of x minus f of 2 over x minus 2. Okay, hello.
Sorry.
Oh, you're good.
Is there okay if I study here for Calc 2?
That's fine. So, okay, so we just need to take our function and plug it into in here. So I'm gonna get this is equal. Oh, actually, let's address right. Tangent line problem. We need 2 things. We need a point and a slope. We already got the point. We got it. Okay, great. Now for the slope. Okay. So. Wow. So we're going to take the limit as x approaches 2 of, so f of x is going to be x cubed minus 2x minus 1 minus f of 2. What is f of 2? 3. Awesome. Over x minus 2. Okay. So we're going to get the limit as x approaches 2 of x cubed minus 2x minus 4 over x minus 2. Interesting. I gotta think about this real quick. So this is so this one's a little different. This actually is factorable. Not I didn't really think it was hard. Okay, anyway, it's not that bad. This is so notice if we plug 2 in, this top part still gives us, we get 8 minus 4 minus 4, so we get 0. So x minus 2 does divide this. So we can always trust in our long lost friend, long division, right? So x cubed plus 0x squared minus 2x minus 4, and divide that by x minus 2. X times what gives me x cubed? X squared, nice. So then I'm gonna have x squared times x squared times 2. And I'm gonna subtract this. So that's gonna give us 2x squared times 2x. X times what gives me 2x squared? 2x. Okay. So we have 2x times x, 2x times minus 2, and then we subtract this. So that's going to give us -2. So this cancels out. We get -2 minus -4. X times 1 gives me 2. Right? So then we just take 2 times x, 2 times -2. And we subtract. Just here. Good. Yes.
Wait, so you know, where do you get the long side?
What is it?
You get the one that goes inside the,
This?
yeah.
So it's this guy. So remember when you're doing long division, you have to add in every missing term.
Okay.
Great. So we get this, okay? So this limit becomes the limit as x approaches 2 of x squared plus 2x plus 2. And I can evaluate this. So we're gonna get, so what's that gonna be when I evaluate that? 10. Nice. Okay, so we have a slope and we have a point. Now we can plug it into an equation. Nice. I wonder if I meant x squared. Interesting. I worked out these problems and I don't remember doing this one. So I'm gonna have to think about it. Okay, anyway, so we're gonna get y minus 3 equals 10 times x minus 2. Right, same equation from earlier. So y minus 3 equals 10x minus 20. So y minus 3 is 10x. Oh, sorry. I'm gonna add y 3 to both sides. Y is 10x minus. Great. So just another tangent line problem, except this one is remembering your definition, okay? So, and long division. Although I will say, long division is important because everybody was talking about what's a slant asymptote. Well, you can figure out your slant asymptote if you remember how to do long division. So. I wouldn't say there's gonna be one that combines all this together, but you might have something like this, and you might have something like the tangent line. It's probably a combo of both. In reality, like I do want to repeat that whenever I made the study guide, I was making it based off of the problems and the homework problems from the book. So if I probably probably thought, I wonder, maybe it was supposed to be, no, it wasn't X plus H. I don't know. I'll have to look at it and think over it. But in the case of what half percentage here, this is how you're supposed to do it. So, okay. Or you can actually pull some magic to factor it, but we won't do that. Okay. We got another one. Yes. Let's go. Okay, which one is it? 33. Okay, this one's actually pretty fun. Okay, sine theta over theta squared. Theta squared. Is that 33?
Yes.
What's the number? Sine theta over theta squared. Minus cosine theta over theta squared, cosecant theta? Yes. Okay. And we want the limit as theta approaches 0? Okay. So we need to evaluate the following limit. Any thoughts? Any ideas? What do we got? What is it? Oh, yes. So plugging it in won't work because this is 0 over 0. And this is, yeah, it's a little wonky. You're going to have 0, might have some weird thing here. You might have infinity, something here. We need to try to fix something here. Okay. So let's take note first. Maybe it would be easier if I rewrote everything just in terms of sine and cosine. I kind of have this pesky cosecant here that shouldn't be there. How can I rewrite cosecant? Not quite, was it? It's 1 over sine, right? Which, in this case, I can just use to say, so I'm gonna have sine theta here, and then I'm gonna have minus cosine theta sine theta. Okay, so that sine theta just comes to the top. And notice once we flip that cosecant up, it's just the theta squared for both of them. From here, we're going to start seeing something awful fishy with this limit. Okay, so I don't see anything right now. Maybe a good technique is always to try to see if I can factor something out or pull something out. Is there anything in common between these two terms? Sine. Cool. So we get the limit as theta approaches 0 of sine theta times 1 minus cosine theta over theta squared.
I see.
Do we see it now?
I think so.
So we have a theta squared on the bottom, right? So everybody knows that theta times theta is theta squared, but I know that theta squared is the same thing as theta times theta. So I'm going to write this as the limit as theta approaches 0 of, and then also I can kind of separate that out. So I'm going to get sine theta over theta times 1 minus cosine theta over theta. Okay, does that make sense? Is that good there? I didn't lose anybody in that, right? That's completely proper. It's okay. Okay. Now, remember from your limit laws that I can take this to each individual piece and work it out. So what is the limit as theta approaches 0 of 1 minus cosine theta over theta? This is 1. Yep. This one is 0. So it's simply 0 times 1, which is 0. Okay, looks bad, didn't it? Promise it's not. Sad. When I came up with it, I kind of just, I think I started out by multiplying them together and then kind of pulled them apart and picked them apart to pull it back down. So.
Wait, can you explain how you were able to divide? I mean, you were able to substitute theta for 0, but like something over 0 is indeterminate.
So yes, but we actually know these two limits. These are famous limits that we know. I'm not going to go and actually this one's not too hard to prove. I'm not going to go into either of them, but these are ones we know. This one is 0 and this one's 1. So yes, it is technically an indeterminate form. But actually, you're in Calc 2, so you're familiar with L'Hopital's rule.
Yeah.
You can't take L'Hopital is technically cheating on this problem because it's technically cheating on this problem because you can't know the derivative of sine to use it unless you know this limit.
Oh.
Fun fact. So yeah. So I know some of you, I'm not sure if it's you guys specifically, but there were some people in the Calc 1 class that used L'Hopital's rule at some point. Were you one of them? I was like, you haven't learned how to use L'Hopital's rule yet. Okay. You used integration by parts on the well, it was a lot of people, like I put a new problem on, so I think there were just certain parts that are like, oh, I missed this little thing. I can completely kind of twist up the problem. Okay. Anyway, let's get back to our discussion here. I'm not sure how much steam you guys have left going. I'm good to go as long as not like I'm not gonna stay here until midnight. Okay. Yeah. I'm running on 2 glazed donuts.
Oh, I saw those.
Yeah. Yep. And I will at some point. Okay. Oh, okay. Oh, we're down to yes. I was like, we're still all in the early ones of my study guide. Let's get down to some lower ones. Okay, number 76. This is actually one of the easier ones. So don't fret. And this is actually a good one to practice because it helps to reinforce what is that? And it's it's on the interval 0 to pi/3. Okay. So I just asked you to write this sum as a definite integral on this interval. And I just asked you not to evaluate it. So how do I write this as a definite integral? We're given our interval. So here's A, here's B. Do we know our function? Tangent x over 1 minus x. Good. That's it.
I did that by myself.
That's it. Yep, no tricks here. That's it. I just wanted you to be able to translate it into I think the book probably had something set up like that, because otherwise I probably would put in like a normal XI or something, but just to kind of see the general form of the integral. Yeah. Mean value theorem. Number 53. Oh, this is fun. Fun fact, this is a function that, or this and like the plus, if I put a plus in the middle, is one that I like to play around with a lot. So that's exactly why it's on here. Okay, so this is number 53. So we want to verify that the function, this function satisfies the hypotheses of the mean value theorem on the interval 4, 9. And then we want to find all numbers C that satisfy the hypothesis. Okay. So I don't expect you to really write out a whole lot or anything to explain this, but it's just to verify. So let's think about it, right? Does this graph have any breaks in it between 4 and 9? No. There's no problems. We'll plug in and they'll all kind of flow nicely together. So this is continuous on that interval. Okay. Is this differentiable on this interval? Yeah. A good way to check this, right? What's the derivative of this function? So it should be something like this. You could write it as 1/2 x to the negative 1/2, right? But then that negative 1/2 will just get pulled down. Okay. Cool. So this is the derivative, right? So whenever we're talking about something being differentiable, you can also think about, is the derivative continuous? Okay. Is this continuous on 4, 9? Yeah, absolutely. When wouldn't this be continuous? Negatives. And that would be the same case for here. What else? So this one actually has a special value that this one doesn't have. 0. 0 is not different. 0 is not a differentiable value because it makes the derivative undefined. Okay, so that's good. It covers our hypotheses, so that means we can use the mean value theorem. Someone give me the mean value theorem.
asking about the word definition?
Just the equation.
That's the. F of A. Oh, yeah, it's F of A minus F of L.
F of B minus F of A over B minus A equals F prime of C. Okay, so let me emphasize here real quick. If this seems hard to remember, slope of the secant line between these two values. Slope of the tangent line, add a number in between them. Okay. Okay, great. So, if you wonder why I picked 4 and 9, it's to make it work out nicely. Okay, so let's calculate those values first. So what's f of 9 going to be? Good, because we're going to take 9 minus the square root of 9, 9 minus 3, which is 6. What is f of 4 going to be? 2. Yes. Good. Okay, so we're going to take f of 9, which is 6, minus f of 4, which is 2, over 9 minus 4 equals f prime of C, right? Now we already have f prime, right? It's this one. So it's going to be 1 minus 1 over 2 square root of C. Okay. 6 minus 2 over 9 minus 4. What's an easier way to say that? Yeah, so it's 4/5. I'm gonna write real quick, just in case for people watching confused or anything. I'm gonna write this is f of 9, f of 4, and then this is which is f of B, A. This is B and this is A. Yes, so I can write that as 4/5. So at 4/5 is 1 minus 1 over 2 root C. Okay. What next? We're solving for C, right? So I'll move this negative 1 to the left side. So we'll have 4/5 minus 1, negative 1/5. 4/5 minus 1 equals negative 1 over 2 root C. Okay. I can make those ones positive. Let's go ahead. Let's see. So I can cross multiply here. Let's just do that. So I'm going to get 2 root C equals 5. So square root of C is 5/2. So let's see. Good. So C being 25 over 4 is going to be the C that satisfies the mean value theorem. Okay. So the slope of the tangent line at 25/4 is the same as the slope of the secant line between 4 and 9. Okay. Cool. Yes. 74 and 75. Gotcha. Okay, so midpoint rule. E. Okay. Here we go. Let's pull out the, well, actually, no, the green can be red. Let's pull out, is that blue work good? Can you start me that? Jeez Louise. Sorry, I got it. But we'll use blue, we can see. 74. Okay. Yeah. Thank you. Oh, yes. Okay, so I want to write an expression for the area underneath the graph. Sign you head now? Yeah, no problem. Thanks for stopping by. So we're going to take the area under the graph, f of x is sine x over x from 1 to 4. Okay, so we want to express the area underneath this curve from 1 to 4 as the limit of the sum, right? Or like the Riemann sum form, right? So essentially, right, we want to think in our heads. Yeah, I technically you shouldn't in this section, but I'll whole lot. It's like not that big a deal. So you should be thinking this at first, right? And I want to turn this into into this. Okay. So turn into this form. So this is what I mean when I talk about the one-loop sum. So f of x is pretty clear. In this case, f of x is sine x over x. What's xi going to be? It's so normally it's well actually not xi first. Let's find delta x first. So delta x is b minus a over n. So we're going to have 3 over n. Cool. What's xi going to be? So xi normally is a plus I delta x. Good. So we have the 3 things we need. So this thing is equal to the limit as n approaches infinity of the sum from I equals 1 to n, always the same thing. So now we want f of xi. So I need to take my xi and plug it into my function. So I'm going to take sine x, sine of xi, which is 1 plus 3i over n, over 1 plus 3i over n, right? Because we're plugging into x in that case. It's x times delta x. Okay, there's ways you can simplify that, but that's completely going to be. Okay, now I was going to ask a question. Oh no, I didn't. Not a question, just a comment. Just please feel satisfied to leave this here. Good luck trying to evaluate that. It doesn't work typically. You can actually evaluate it if it goes from, I think it's 0 to infinity. It's going to be pi over 2, but not using standard methods at all. So, great. So that's our limit. Okay, that good there? So that's number 74. Did you still want to do 75 as well?
Yeah.
Okay. So I'm gonna so 75, let me address real quick, right? Is a similar vein as a couple of earlier problems, which are doing left endpoints and right endpoints, right? In 4.2, they introduced the concept of midpoints. So instead of using left or right directly, we're using midpoints instead. So, but we still start out in the same fashion, right? So we're using the midpoint rule to estimate the integral from 0 to 8 of x squared plus 1.
Thank you. And good luck, guys.
Yeah, thank you. Square root of x squared plus 1 dx when n equals 4. And we want to use midpoint. Ooh. Great. So if we're using midpoint rule, right? What do I need to find first? What is it? Delta x. Good. How do I find delta x? Good. So now again, I'm going to draw kind of like I did in class earlier today. So we're going to have 0, 2, 4, 6, 8. Right. So now we want the midpoints, right? So what values do I use in this case? We use, what is it? We're going to use the numbers in between each integral, the exact middle point. So between 0 and 2, the halfway point is 1. Between 2 and 4, halfway point is 3, halfway point is 5, halfway point is 7. Okay. Now, obviously, this isn't one that you can calculate in your calculator still, but 1 squared plus 1 is still root 2. It's still not a, yes.
What if it's three notes?
What is it?
What if it's three notes?
If 3 in here?
No,
No, because like the delta X would be.
Oh, you wouldn't have that. In this case, delta X wouldn't be 3. Now you could have it if we went from 0 to 9 and then n was 3, then you could have delta. But so in that case, so let me suppose, so let's say we're going, so we have 0, 3, 6, 9. Okay, so we have 3 boxes. Okay, and you want the midpoint of each box. Then you're gonna take 0 plus 3 divided by 2. Which is 3 halves. 3 plus 6 divided by 2, 9 halves. 6 plus 9 divided by 2, 15 halves. Same thing that happens here. 0 plus 2 divided by 2 is 1. 2 plus 4 divided by 2 is 3, etc. Okay, so then our area is going to be approximately delta X is 2 times f of each of these 4 values, right? So we're going to have f of 1 plus f of 3 plus f of 5 plus f of 6. Which is going to be 2, and then you can plug in each of the numbers. 1 squared plus 1 is 2. 3 squared plus 1 is 10. 25 plus 1 is 26. And 49 plus 1 is 50. Okay. And so that would be the midpoint. Okay. Can't get an exact answer, but that's approximately the rate. Okay. Cool. So there's midpoint rule. Okay. You heading out?
Thank you for.
Yes.
fixing these also now.
Yeah, no problem. It's been really good. So I'm happy to help out. All right. What we got? Give it to me. 78. Okay. So it's a good spot of questions apparently. These 75, 78. Okay, so we're wanting to find the derivative of g of x, which is the integral from 5 to x squared of 1 over 1 plus t. Okay. So, and this question specifically says to use part 1 of the fundamental theorem of calculus to solve this. Do we remember what part 1 of the fundamental theorem of calculus says? What is it? He said negative. Okay. The first part says that to generalize it more, actually, the theorem itself says that if I have g of x is the integral from a to x of f of t dt, then g prime of x is f of x. That's the first part of the fundamental theorem of calculus. Right? So essentially the derivative of that integral just puts that thing that's on the integral into the function itself. Okay? So if I'm finding g prime in this case, what's that going to be? Right, so following in this example, looks like we just take we take the x part and we put it in, right? So I'm gonna have 1 over 1 plus x squared. Okay, but notice this is not x, we have x squared. To account for that, I multiply by the derivative of x squared, which is what? 2x. So it's going to be 2x over 1. Okay. Now, for those asking here, I'm sure you might have a question. Why do I ignore the 5?
It's not- I don't actually know. I know why I would.
So yeah, so let's appeal to answer that. Let's appeal, maybe it's a little easier to see. Let's go to the second part of the fundamental theorem of calculus, which says that the integral from a to b of little f of x dx is its antiderivative evaluated at b minus its antiderivative evaluated at a. Okay, so in this case, let's say that you know, the integral of 1/1 plus t dt is, and I'll use, I don't know, g, no, not g. I'll call it f of t. Okay, so this has some certain antiderivative, right? Now, when I plug in the values, then the integral from 5 to x squared of 1/1 plus t dt is going to be f of x squared minus f of 5. Okay, now keep in mind, this is just a number, and this is a function, right? Because it has x squared still in it. Okay, so when I'm taking the derivative of this thing, and this thing here is g of x, right? I'm taking the derivative of f of x squared minus the derivative of f of 5. What's the derivative of a constant? 0. So that becomes 0. And then the derivative of big F, right? This requires chain rule. So the derivative of big F is little f. So it's going to be little f of x squared times the derivative of the inside, because we have to use chain rule. Again, because we have x squared inside instead. So that pops out of 2x. But f of x squared is 1/1 plus x squared, so we get 2x. Okay, it's really more simple just to go through this method, right? Of course, but I want to explain why I can ignore the 5 and what exactly happens. Okay, so feel free to use both, kind of, they're at your disposal to be able to figure it out. Okay. I thought this is the water tank problem. I was like, I don't know if I'm still fine to go, but I'm not sure if I'm that ready. Okay. So this is the last lesson you learned, which is about average value. So I want to find the average value of my function, of the function. So I want to find f of x equals the square root of x minus 1 on the interval 2, 5. Okay, so let's start with that. How do I find this? So integral from a to b of f of x dx, right? So a and b are 2 and 5 respectively. So we're gonna get 5 minus 2. So 1/3. Integral from 2 to 5 of the square root of x minus 1 dx. Okay, now typically we would have to do u sub on this, but I say why bother? Because it's only a minus 1. You can just treat this like x. That minus 1 isn't going to do anything. If you like where you need to? Okay, so if I would suggest you do that if you had something like this. Okay, because that one's not so clear. That one gets absorbed, right? This one's not going to do anything. This one has to get absorbed in. Okay.
The square root of x squared minus
Well, not the square root part, you would just substitute. You would say u is x squared plus 1,
one.
the inside. So d would be 2x dx. And then you would infer from there.
Gotcha.
In this case, it doesn't matter, okay? Because that minus 1 isn't going to do much for you except just be a hassle to have to try to pull it back later. So this is the same thing. How do we integrate? Okay, let me ask, how do we integrate the square root of x? That's taking the derivative. I want to integrate it.
The same thing, actually.
So I want to take the integral of the square root of x dx, which is the integral of x to the 1/2 dx.
So what's three?
So we're going to get x to the 3/2 power over 3/2 typically, right? Which we can, right, this is 2/3 x to the 3/2. Okay. And that's going to apply here. That minus 1 I said, like I said, doesn't affect anything. So this is going to be 1/3 times 2/3 x to the 3/2 power, or sorry, x minus 1 to the 3/2 power, evaluated from 2 to 5. Okay. So what's so we're going to get 2/9 times 5 minus 1, 4 to the 3/2 minus 1 to the 3/2. 1 to the 3/2 is easy. It's just 1. Anybody have a guess at what 4 to the 3/2 is? Bless you.
This always confuses me. I'll show you that. Six. Wait, no.
Not quite.
No.
So we take, so 3/2 means that I take the square root and then I cube it.
I was
So the square root of 4 is 2, and then 2 cubed is 8.
trying to multiply by it.
Gotcha. So we have 2/9 times 7 essentially, so this is gonna be. So that is the first part of the problem. The second part says to find a value C. Find a value C on the interval such that f of C is equal to at that. That is, f of C is equal to 14/9. Yep. This is kind of like mean value theorem for integrals, right? So you're saying that there's a certain f value that if I integrate these two, if I look at the average here, I can just get the same value. So I'm going to do the square root of C minus 1 equals 14/9. So C minus 1 is going to be 196. 81. So those are just, I mean, you can always work out 14 squared and 9 squared, but that's all that ends up being. So then C is going to be 1 plus that. So 196 plus 81, 7, 1, 2. So C shouldn't have been 277 over 81. Okay, so that's simply from just solving this equation. The numbers are a little big, but nothing too bad. Okay, finally, I just want to sketch a picture of what the graph looks like and a rectangle that has the same area within that interval. So I'll draw that over here. So what does the square root of x minus 1 look like? kind of a, yeah, it's kind of a sideways parabola, right? And it has to start here at 1. Okay, and then we're saying we want to look at what the area. So we're saying it has a specific area between 2 and 5, right? Which looks something like this. Let me just kind of box in the area here so you can see it. I'll put in some lines. Okay. And then we're wanting to say, okay, well, there's a rectangle that I can draw within the same region that has the same area. Okay, which looks like, which probably end up looking something like, I don't know, you have to get kind of close to 277 over 81. But we'll say it like that. Okay. And so that's kind of the ultimate goal of F average, is to kind of see that comparison, that we can just get a rectangle of that same area instead of like, rather than, you know, kind of seeing the area as it is there. Okay. Cool. Okay. So you're heading on out? Yep.
As soon as I start seeing.
It's probably about time. You're all the questions? Great. Someone, you got any more questions for me? 2 more questions. Gotcha. Yes, no problem. Have a great night. Evaluate the indefinite integral. Okay, so. Okay, so this is what test is this? Is this on? So I can mark it for people. Fall 17, number 13?
Yeah.
Okay. Fall. I just used it. It's fine. Okay. So, and it's the integral of square root of 1. Wait, the 1 minus square root of x? 1 plus square root of x?
Yeah.
Which one is it?
Yeah. 1 plus.
1 plus?
Yeah.
Squared over square root of x?
Yeah.
Okay, so there's a couple of ways that I would think about doing this. You could go and try to do u sub, but my advice would be, this isn't that hard to square. We can square that, right? Either you guys know what this is going to be squared. 1 plus x, good. There's a middle term, right? Don't fall into the, remember, x plus y to the n power is not the same thing as x to the n power plus y to the n power. Okay, we need a middle term. What's that middle term going to look like? 2 times the square root of x. Okay, perfect square. And this is all divided by the square root of x. Yeah. Okay, now why did I want to do that? Why is that useful to me? What can I do with this square root now? What is it? I wouldn't multiply right now. But it's only one term, right? So why don't I just take it and divide it from each guy? So we'll take it and divide it from 1, which leaves us with x to the minus 1/2. We'll take it and divide it from the 2 root x, which leaves us with 2. And we'll take it and divide it from the x, which leaves us with just an x to the positive 1/2. Yeah. Okay. No confusion on the 1/2 or anything here. I just kind of flipped it. Okay, so what's the integral of x to the minus 1/2?
0.
Not 0, right? Remember, so power rule for integrals says that I add 1 to the power. What's the negative 1/2 plus 1? The integral. So we do x to the positive 1/2 power over 1/2, and I'll leave that for now. Plus, what's the integral of 2? Good. What's the integral of x to the 1/2? We actually already did this one earlier. I'll go ahead and write it down. 2/3 x to the 3/2.
Yeah.
That was for the average value problem. Okay, now, how can I rewrite x to the 1/2 over 1/2?
That's 2x. 2x and a first part.
Plus 2x plus 2/3 x to the. All right, am I done? No? We got the integral, right?
Yeah.
What's wrong? We're not done. What about the plus c?
Oh.
Can't forget about the plus c. You're gonna get your points taken off if you don't put a plus c.
That's only for indefinite.
Yes, if it's indefinite, then it needs a plus c. Okay. So there's number 13, fall 17. Not too bad, just square, divide, and some wrong power rule. All right, you got one more question. Or you got a, okay.
Is this somewhere of course?
Okay.
Yeah. So,
Oh, is curve sketching?
yeah.
We didn't get to cover that today. Wow.
So, yeah. Let me just. I don't want to give an example.
So you have critical points like 1 and 7 as an example. Okay, I'm rolling with you. Or 1 and 2. That's good. Okay, inflection. Okay, wait. So the hold on, let me read this. Are these the x values or is this like a point?
No.
Okay, those are x values. Gotcha. Thank you. 2, 3. Okay. Interesting. Okay.
So these, oh, you still need the original function.
What is it?
You still need the original function.
Okay. Wait. So are you one? So we're given these. Okay. I'm sorry. Wait. So we're given these. Are you saying we're given these?
Yeah.
Okay, and we're wanting to construct the original function out of it. Gotcha. Okay. So let's say we're given these, and we want to make the function out of it. Okay. Now, this is this could vary a little bit because it depends on kind of if your function's concave up or down at a certain point. Okay. Well, let's say we were only given this information. Okay, to curve sketch. Okay, that's completely fine. Let's take. So we have critical points, x is 1, 1, and 2, and inflection points at 2 and 3. So let's address those horizontal and vertical asymptotes first. So we have a vertical asymptote at 2. So it'll look like that. Okay. Now, okay. So I'm gonna assume, right? I don't know if you meant to do this, but we have an inflection point, quote unquote, at 2, and we have a critical point at 2. But notice those are points where we have nothing, right? Because it's a vertical asymptote. And so those probably break the function, right? And that's okay. So those are critical points because they're at the vertical asymptote. So we don't need to consider those. All we need to do is think about, okay, I have a critical point at 1, okay, and I have an inflection point at 3. Okay, so if I have a critical point at 1, and I have this horizontal asymptote, right? That tells me that our function is probably gonna. I can either have a max or a min at that point. Okay, so let's say that I have a min. Sure, why not? Actually, maybe. No, because okay. This is kind of a maybe the horizontal asymptote. Okay, so let's say we have a minimum of 1. Okay, at 1. So our function would have to look something like so. This is its low point, and then it picks back up. Okay, assuming that critical point is the minimum. I think that makes more sense in the graph. I could be wrong, but of course we're not completely sure here. Now I don't have any critical points over on this side. So I don't have to worry about any sort of max or mins over here. But I do have an inflection point, which means that my concavity changes, right? Here, I didn't have to worry about that. I just made it concave up the entire time. Here, I do, because I have an inflection point of 3. So that means that, so let's say 3's here. That means I need to change from being, let's say that I am, so I'm concave. Yeah, let's say I'm concave down up until that point, and then I need to be.
Oh, so just because it's not a critical point, doesn't have to touch that, one of the axes.
Right. Okay. I will say, I think some of these might be at odds with each other. Yeah, and that's fine. That's fine. But that's the idea you want to take away, is being able to say, okay, and it'll be even easier to kind of guide once you can piece things together easier. But you want to be able to say, okay, well, I have my critical point should be a max or a min. Now, sometimes the critical point in the case of x cubed, as an example, x cubed has a critical point at 0, but it's still increasing afterwards. It just slopes off so much. So that's something to consider also. And then inflection points can technically not be inflection points either. But generally that's, you want to be tracking that sort of thing. So does that answer it pretty well, I think? Okay, awesome. Cool. You don't know. Oh, yep. Cool. Well, I'm gonna have to get that downloaded and get that uploaded as soon as possible. So yes, we are running on 3 hours right now. I guess I should end it. Thank you all for watching. This has been very long. I hope it's helpful. I think I did manage to list every problem up there, so you know which one we're doing. But again, I hope it's helpful. I've enjoyed being your recitation leader for you who are in my recitation this semester, and for all those who weren't, I'm happy to provide some resources to help out. So anyway, have a wonderful day. Yeah, thank you very much. Bye.